I'm Gabe Angelini-Knoll. I am a postdoc at Michigan State University, and you'll see what I think about. But I think about questions in the intersection of algebraic K-theory, chromatic homotopy theory, and a little bit of equivariant homotopy theory more recently. So let me share my screen, and we'll get started. How's the volume? Should I talk a little louder?
Seems fine.
Okay. Everyone see that? Okay.
Yeah, we can see it fine.
Great, thank you. Okay, so I'm going to talk about iterated algebraic K-theory of the integers and higher Lichtenbaum-Quillen conjectures. So first, to just get started, let me just say what I mean by algebraic K-theory. I'm not going to give a precise definition, but so algebraic K-theory is going to be a functor that classically it takes as input a ring and then has output a graded abelian group. But after Quillen and maybe Siegel, we saw that really we should think of it as factoring through spectra. And then the algebraic K-theory groups are then the homotopy groups of that spectrum. And so I'm going to talk about, so you can generalize rings to ring spectra. And then I'm going to talk about a special case, really, for most of the talk, so where we have a commutative ring spectrum as input. And then the output then is also going to be a commutative ring spectrum, and then a graded ring. So we'll write K of R, where R is a commutative ring spectrum. And if we take the homotopy groups, sometimes we'll also write a K lower star of R for the homotopy groups of that spectrum. Okay. So first, so I want to talk about iterated algebraic K-theory of the integers and higher Lichtenbaum-Quillen conjectures. So first I should say a little bit about the classical Lichtenbaum-Quillen conjectures. So I'm going to start with Lichtenbaum's version of these conjectures, which is the following. So we're going to have to set, let's let F be a number field with ring of integers OF. Then Lichtenbaum conjectured, so I should also say, let's say a totally real number field. Then Lichtenbaum conjectured that if you look at the degree 4k plus 2 group of algebraic K-theory of O of F, you take the order of that, and then you quotient by the order of k 4k plus 3 of O of F. Then that should be equal to zeta F negative 2k minus 1 up to, so this is really up to sine and power of 2. Okay. So I realize this is a homotopy theory audience, and so not everyone will be familiar with these zeta functions. So let me just give a brief definition of that. So if you take zeta of F sub F of S, that's going to be the sum over all ideals contained in OF of the order of OF mod I, and then you take that to the negative S. And that's how you define it for the real part of S greater than 1. And then you analytically continue so that you get analytically continue to get a meromorphic function with simple pole at 1. And then, so these are how it's defined for positive integers. But then the values we really care about more are the special values, which are these values at negative integers. And so it's really a theorem that for a totally real number field that these are actually rational numbers, and then you can compare to the orders of these K groups.
Gabe, this is Dan. I have a question which maybe, you're not equipped to answer, and that's fine. But, I've always wondered, like, where does this conjecture come from? Like, do you have, I've never been able to sort of imagine what kind of evidence or whatever there could be for something like this. And especially with the up to a powers of 2, right? I mean, so why?
Yeah.
Anyway, so.
Right. So let me give an answer to that. That was going to be the next thing I was going to say anyways.
Okay, great.
But yeah, certainly there's probably more behind this than I know about it. But yeah, so some evidence for this actually came from homotopy theory. So let me talk about that, and hopefully that will sort of answer part of your question. So let's look at a special case when f is equal to the rational numbers. Then if you look at the unit map from the sphere into k of z, and then you look in degree 4k plus 3, then if you look at the image of j part sitting inside here, then it turns out that that includes into this algebraic k-theory group and actually splits off. And so this is really by work of Quillen and Sullivan. And then you can then invoke work of Adams, which says that the image of J in degree 4k plus 3 is equal to, again, let me just be careful and say up to a sign and a power of 2. It's equal to the denominator of the Riemann zeta function at negative 2k minus 1. Okay, so this was some of the first evidence for that conjecture. Lichtenbaum mentions it in his paper as some of the first evidence, and it really came from homotopy theory. So I want to make the case that these conjectures about arithmetic information and in algebraic K-theory of rings is really deeply connected to homotopy theory, and so we should try and explore that further. So, right. Okay. Yeah, and then let me just also say a little bit more about this image of J. So if you just look at the part corresponding to a particular prime P, then that actually corresponds to that corresponds to the homotopy groups of a certain spectrum. So let's look at these groups here. Then this is isomorphic to Z mod P to the p-adic evaluation of K plus 1. And inside here you have the divided alpha family, which, so this divided alpha family is really closely connected to the zeta function. So here we have alpha K, let me just say over J, yeah. So you have this divided alpha family, and that corresponds to these denominators of special values of Dedekind zeta functions. So this sort of hints at a dictionary that I'd like to pursue further. So you have here just homotopy theoretic information and number theoretic information. So if you look at V1 periodic elements, so for example, the alpha family, then the idea is that should correspond to zeta functions. And specifically, we see the Riemann zeta function here. And then there's a little bit of work for V2 periodic elements. But I think even here, there's more to be said. So for example, the beta family is known to correspond to certain modular forms. And this is by work of Behrens. And then you could try and extend this further to V3 periodic elements. So like the gamma family. And maybe there's something to say about the connection between that and automorphic forms. I think that would be interesting. I mean, that's kind of like what you would expect, but I don't think there's any explicit description of the gamma family in terms of automorphic forms yet.
So when you're saying V2 periodic elements and beta family, so Andrew Salk sort of very often, when I'm talking to him, and not that I understand this, but he very often sort of wants to make a distinction between the beta family and the V2 periodic elements, right? So which are the ones that correspond to modular forms? Is it the beta family really that corresponds to modular forms, or?
I guess so. Right. So the beta family is what is known to correspond to modular forms by Barons, but I guess I would like to suggest that possibly other V2 periodic elements could be related to modular forms as well.
Okay.
And I'll say a little bit more about what happens for V1 periodic elements. But so far, what we've said is that the alpha family corresponds to the special values of the Riemann zeta function.
Okay, thanks.
And also I should mention Andrew, since you brought up Andrew, he has also a different take on this, that maybe you could relate these kinds of V2 periodic elements and V3 periodic elements to maybe special values of L functions of higher period or something like that. But you should ask him about that. That's not something I know too much about. Okay. So, right. So then I just wanted to say a little bit also about the Quillen-Lichtenbaum conjecture and how you might try and prove Lichtenbaum's conjecture. So I'm going to give a kind of more modern take on that. The idea is to look at the relationship between a tau cohomology and algebraic K-theory. And so you have actually a map of Atiyah-Hertzberg type spectral sequences. And you can use that to try and study the difference between algebraic K-theory and a tau cohomology, or see what parts of algebraic K-theory are detected by a tau cohomology. So let me just fill in some of the details here. So we're going to look at spec OF, and then we really need to invert a prime here, and then look at with coefficients in the pth roots of unity sheaf, and then take tensor powers. And then there's a spectral sequence here that converges to V1 inverted S mod P smash K theory of OF 1 over P. And this spectral sequence is really due to Thomason. And then here we have spec of OF 1 over P coefficients in this Navik sheaf that you can read about in Voivodsky's work. And then, so algebraic K-theory satisfies this Navik descent. So that tells you get a spectral sequence like this. And then we have mod P as well here. Okay, so then the Lichtenbaum-Quillen conjecture, or the, Lichtenbaum-Quillen conjecture can be phrased as saying, is this an iso for a star sufficiently large? And really, you have a precise bound corresponding to the cohomological dimension of this affine scheme, but let me not go into that. So, right, so this is the Lichtenbaum-Quillen conjecture. And so this was proven, so really both of these results, I should mention that both of these conjectures have now been proven. And the key step in the proof was due to Voivodsky and Rost. And essentially, for this conjecture, what you do is you show that this input is an isomorphism in a range. And then that is going to imply the conjecture. Okay. So that's all the classical Lichtenbaum-Quillen conjecture. Now I want to get into higher Lichtenbaum-Quillen conjectures. Okay, so this is really code for the Redshift conjecture. So let me just state the Redshift conjecture of Osoni-Rognus. So let's suppose that, if R is a suitably finite K-n local spectrum, then the conjecture is that if we smash algebraic K-theory of R with some type n+1 spectrum, and then we map to the Vn plus 1 inverted V smash K of R, then this is going to be an ISO for star sufficiently large. And so I should say for V a type n plus 1 spectrum. So if you don't know what that is, let me just say really quickly. So that means that if you take this Morava K-theory, cohomology theory, and you apply that to V, then it's non-zero. But if you apply Kn star to V, it's 0. And by work of Hopkins and Smith and building on Hopkins, Devnot Smith, you know that if a spectrum has this property, then it's going to have some Vn plus 1 power self-map, and you can take the colimit over those Vn plus 1 self-maps, and that gives you this object. And so, yeah, so let me not say more than that. Okay, so at the time, what was their evidence for that conjecture? Let me just say a bit about that. So they showed that V1 star of the algebraic K-theory of the atom summand is a finitely generated polynomial on V of 2 module. So this, this computation implies this statement here where V is equal to V of 1. And let me just say that V of 1, you can think of that as first cone off P and then cone off V1. So I should say here really P is greater than or equal to 5. Okay, so why is that evidence? Well, so if you look at the localization sequence, so this is due to Bloomberg, Mandel. Then if you look at, so here let's say if a spectrum has this property, then we say K of R has telescopic complexity n plus 1. So basically you look at this localization sequence, this has telescopic complexity 1, this has telescopic complexity 2, so that implies that this has telescopic complexity 2, and then L is a Galois extension of the K1 local sphere. So L is a S1 Galois extension of the K1 local sphere. So really for their definition of suitably finite, you would want it to be a finite Galois extension, and this is a profinite Galois extension, but this is their evidence for the conjecture. Okay, so then this is kind of like the state of knowledge in like the early 2000s. So I want to present a slightly different version of this conjecture. So I call this the Greek letter family redshift conjecture. And I'm just going to state this in a special case. So the idea is the nth Greek letter family alpha upper n is detected in the Hurevich image of k iterated n times of z. And really what I will show is this when we p-complete at each stage for a specific case. Okay, so, right, so this conjecture I think is more closely related to the original Lichtenbaum conjecture. That's, yeah, one reason why I like it, I guess. So for example, the beta family is really detecting some number theoretic invariant. And so you'd like, so yeah, so I think it's a little bit closer to the original Lichtenbaum version of the conjecture. Okay, so I wouldn't give this conjecture if I didn't have some new evidence for it. So let me talk about that. And actually, maybe even before I do that, let me say about evidence for this conjecture that was already known. So let's say n equals 0 and 1. So then if you look at the map from the p-complete sphere spectrum, so the first case is kind of trivial, right? If you don't iterate K3 at all, then you just have the Eilenberg-MacLane spectrum p-completed. And then what I'm calling the 0th Greek letter family is just the elements p to the k. And clearly those map non-trivially here. Okay, so that wasn't that interesting. And then if you look at k of z and p complete, you have a linearization map from k of z to hz because pi 0 of kz is z. So then you can look at this map, and then as we saw, alpha p over k is not equal to 0 there. So if you look at the divided alpha family is not equal to 0 there. So that's by this stuff we saw from Adams and Quillen and Sullivan. And then the next stage would be to look at k of z, and homotopy groups there. Okay, and then you can keep iterating this. Okay. All right. So that's the state of knowledge, and then so let me say the theorem. So the beta family is detected in the Horevich image.
Sorry, Gabe, I have a quick question.
Can I just finish the sentence real quick?
Oh, sorry, yeah.
So the beta family is detected in the Horevich image of k of z. Okay. Yeah, so what was the question?
So when you iterate k, you keep p completing at each stage, but why are you not taking k of zp when p completing?
Yeah, so you could do that. I guess I chose not to. I mean, so I'm just taking k of z on the p is on the outside. Yeah. So there, I guess like here it's maybe unclear, but really I'm thinking of this as k iterated 0 times and then p completed.
Okay, that makes sense. Thank you.
Yeah, great. Okay. Great. Okay. So this is, yes.
This is Prasid. I have a question too. So can you go back to the diagram?
Yeah.
So is there always a map from k of something? I mean, if I take a spectrum x, then I have a map from k of x to x.
No. Yeah. Not true.
Not necessarily. So this is not a there are no arrows from k of z to k of z.
No. In this case, you do. You don't have it in general, but in this case, you do have it.
Oh, okay.
So yeah, because if you look at k0 of z, that is actually isomorphic to z. And so then you take the map, you just kill higher homotopy.
Oh, I see. So I see. So then you apply the k function. Okay, gotcha. Is there anything said about like the inverse limit of all the k's? Of just curious.
I think that would be an interesting question to study. I don't really know, what you can say about that, but
okay.
Yeah, I think that's interesting. I mean, yeah.
Okay, thanks.
All right. Yeah, so first of all, I should say that really so I said it as a theorem, really it's a corollary of another theorem. So let me state the theorem, and that will kind of lead into the method of proof. So the beta family is detected in k of fq when q is a generator of z mod p squared cross. So that implies that it's a topological generator of the p-adic units. And also we're going to assume that p is greater than or equal to 5. So actually here we also assumed p is greater than or equal to 5. So there's some ambiguity in the way I stated the original conjecture because these Greek letter family elements are not always known to exist. But basically I want to say like when they are known to exist, then they're going to be detected. So here the whole beta family exists at p greater than or equal to 5. So there's not a problem there. Okay, and then I want to actually refine this even further. So the real theorem is proven actually not about K-theory, but about topological negative cyclic homology. Okay, so this is an object.
Did we lose Gabe's connection?
I don't hear anything from him.
Yeah, okay, me neither. Okay.
All right, so then let's move on, I suppose. Okay, so the idea is we want to show this, and so what is this object? And I want to introduce trace methods basically to discuss that. So let's talk about trace methods. This is going to be a very quick and dirty approach to trace methods, and I'm also going to take the more modern approach, which we have after Nicolaus Schulze. Bear with me. So let's say R is a commutative ring spectrum, and let's say connective. Although that's not a major assumption, but I'll say where it's used. So we take a connective commutative ring spectrum, then you can approximate algebraic K-theory by topological Hauschild homology. And there's a couple ways of thinking about what that is. So you could think about that as R smash over R smash R op with R, or here it's commutative, so the op doesn't really matter that much. But really I want to think about it as S1 tensor R in the category of commutative ring spectra, because then it's more clear to see how the S1 action comes into play. So you can act on S1 on this coordinate, and then you get an S1 action on this spectrum. Okay, so then you can form topological negative cyclic homology. And what is that? Well, topological negative cyclic homology is the homotopy S1 fixed points of THH of R. And then there's another object that comes into play, which is topological periodic cyclic homology, and that's the Tate construction of S1 on R. And so basically, so you can look at this equalizer sequence, and there's a lot hidden in these maps here, but there's some Tate valued Frobenius map, and there's a canonical map, which I'm not going to say much about, but these come into play because of the cyclotomic structure on THH. And so you can take the equalizer of those two, that gives you topological cyclic homology. And then really I'm talking about the P-complete story on the outside here. But then in that case, then these are very close. And in fact, for the spectra that we'll be talking about, they'll actually agree after taking connective covers. So that's pretty nice. Okay, so that's a very quick and dirty introduction to trace methods. Apologize if that's your first time seeing it, but so the object we're going to be looking at in more detail is this. Okay, so let me give a more precise, actually, model for this. So I guess these are definitions. Okay, so this is going to be defined to be the function spectrum from ES1 plus into THH of R, and then you look at the S1 fixed points of that. So ES1 is a contractible space with a free S1 action, and then this is a model for the homotopy S1 fixed points. Okay. And actually, I'm going to specialize to the spectrum we care about, K of FQ, be completed. I'm just going to keep those assumptions on Q and P throughout. Okay, so then this we can rewrite as, so we can write this as a colimit over its skeleton, and then we can pull out the colimit as a limit. And I just want to give this object a name. That's why I'm bringing this up. So let me call this whole thing just TK. And then we're taking the limit of that. So this TK is gonna come into play later. So hopefully try and keep this in the back of your mind. Okay, so then actually the further refinement is that the element beta K is detected in V1 star of tk plus 1, or in the, actually, let me say it the same way. So in the Horevich image of v of 1 smash tk plus 1. Okay, so this is going to be the further refinement of the theorem that we want to actually prove, which will imply the rest, as I'll say at the end. So how do you prove that? So let me give the first part of the proof sketch, and then I'll need a brief digression. So the first part of the proof sketch is the following. So this was inspired by Alsoni and Rognus, something that they do in one of their papers. So the idea is to look at the unit map from the sphere to v of 1 smash tk plus 1. So yeah, I didn't mention this yet, but actually if you input a commutative ring spectrum, then actually all of these tks are going to be, again, commutative ring spectra. And then this is also a commutative ring spectrum. So this is observed by Brunner and Rognus, but yeah. So and then v of 1, we're at a prime greater or equal to 5, so v of 1 is also a ring spectrum. So we can look at this unit map. Okay, so then the point is that this unit map, which is going to induce the, it's the Horevich map, right? So this is going to induce a map of Adams-Novikov spectral sequences, or BP Adams spectral sequences. So I'm not going to write the first coordinate. The first coordinate is going to be BP star. I'm just going to write x BP star BP star, x BP star BP of BP star, mapping to x BP star BP of BP star v of 1 smash tk plus 1. Okay, so the idea is going to be to trace the element beta k through this map of spectral sequences. Okay. All right, so that's going to be the goal, but to do that, we need to know what this object is. And we also going to want to know a little bit about v1 star of tk plus 1. Okay, so that's going to be the kind of intermediate goal. And so to study this, I'm going to have to do a bit of a digression and talk about some other work. So bear with me. So we're going to take a brief break for this proof and then come back to it. And yeah, so the goal now is to compute BP star v of 1 smash tk plus 1. Okay, so in particular, BP star, when k is equal to, or when k is equal to -1, I guess, this is, we want to understand a THH of k of fq be completed. So this is going to be the first step. Okay. So to do that, I want to talk about some joint work with Andrew Stalch. Okay, so the idea is to use a filtration of a commutative ring spectrum, a multiplicative filtration, to filter the cyclic bar complex and then give it a spectral sequence in THH. So we need a definition of a filtered spectrum. So a multiplicatively filtered commutative ring spectrum. So I'm going to give the very bare bones structure. So it's a sequence of maps and a sequence of spectra. And with structure maps, rho ij from I smash ij to I plus j. And so these have to satisfy some axioms. And one way to package this whole object in like a very succinct way is the following. So you can think of I dot as is a cofibrant object in the category of commutative monoids in the functor category from the natural numbers up to spectra. So I'm using the facts theorem due today, which says that this is equivalent to lax symmetric monoidal functors from the natural numbers op into spectra, because that's really, this is like the lax symmetric monoidal structure. But then you use this equivalence, and that allows you to give a good a model structure on this, in which the objects we care about are really the cofibrant objects. But in particular, we want each of these objects to be cofibrant and all the maps to be cofibrations. And also, I should point out that I0, if you have this structure, I0 is going to be a commutative ring spectrum, where rho 0, 0 is the multiplication.
Sorry, I have a question. It's Sean.
Yeah.
Each of these spectra in the filtration, these are commutative ring spectra, or is it only as a filtered object? Does it have a monoidal structure?
Yeah, great question. So yeah, it's not true that each of these objects are a commutative ring spectrum. Only I0 is a commutative ring spectrum. So only when we start with as a filtered object is it a commutative monoid. So really, we think of these I's as like filtered by powers of ideals. So.
Okay, thanks.
Yeah, thanks. That's a good question. Okay. Okay, so then, right. There's also an associated graded, which I'll just write like that. And so, so there is an associated graded commutative ring spectrum, which is like this with underlying spectrum given by this big wedge I greater than or equal to 0 of II mod II plus 1. So that's sort of what you would expect for associated graded on underlying spectra, but then you can build it as a commutative ring spectrum. Okay. All right, so then let me just state the most general version, or it's actually not even as general as we have it in our paper, but it's almost the level of generality of the paper. So, so you can actually tensor with any simplicial finite set, and you'll get a spectral sequence converging to the homotopy groups of x dot tensored with I0. So this is any simplicial finite set. Finite set. And then the second grading is coming from the May filtration. Yeah, we think of this as a kind of May spectral sequence. Yeah, because it's built in a kind of similar way. Okay. All right, so if all of that was a little bit too abstract, let me get a little bit more concrete. So
I'm sorry, can I ask another quick question?
Yeah, absolutely.
About this spectral sequence?
Yeah.
I might have guessed that you tried to compute this by using the skeletal filtration on the simplicial set, but you have an inverse system that you're taking the associated graded of.
Right.
Okay, but this is I0 on the right.
Yes. I
So you have an inverse system, but you're taking the co-limit of it somehow, right? Because this is like how Bob does the atom spectral sequence.
I mean, depending on your conventions, you might think of this as like a negatively graded.
Yes, exactly. Yeah.
Well, so let me just say, a few more words about the construction. So basically, like a priori, you would have a spectral sequence. So you have like maybe I'll draw a little picture here. So you have this picture where you have like a filtered simplicial object. Let me not fill in what's here, but so you get this filtered simplicial object, and then you take the associated graded of that in filtered objects, and that will give you the input for the spectral sequence, and then you have to show that that associated graded is the same as this object, and that was like the main theorem in the paper, but then that turns out to be true, right. So that's kind of like where it's coming from a little bit more. Hopefully that's helpful. Okay. All right, so yeah, let me continue. So yeah, so if this was a little bit too abstract for you, let me get a little more concrete. So this is an example / theorem. So, I'm going to give an example of a filtered commutative ring spectrum. So basically you take R, a connective commutative ring spectrum, and then you look at what's normally called the Whitehead tower. Right. So this part you can build without too much trouble, but then what we do is we build this in a structured way so that you have structure maps tau I greater or equal to I R smash tau greater or equal to J R to tau greater or equal to I plus J R. So, right, so yeah, I should say what these objects are. So this spectrum on homotopy groups, it's just the same as R in degrees 1 and higher, and then below it's 0. So, so this is really the same as tau greater or equal to 0. Okay, so so this is a filtered commutative ring spectrum in the sense, the precise sense I said in the definition. Okay. So, and then the associated graded is also particularly nice in this case. Then you have R tau greater equal to dot R. This is H pi star of R. So you look at it's the generalized Einberg-MacLane spectrum associated to the graded ring pi star of R. So it looks like H pi 0 R, wedge H pi 1 R, and so on. Okay. All right, so then kind of special case is the following spectral sequence. You can look at THH of H pi star of R, and then take homotopy groups, so really any connective generalized homology theory, and that's going to converge to pi star of THH of R. Okay, so that's going to be the version of the spectral sequence that we'll use. And right. Okay, so now, okay, so that little aside, let me remind you of the goal. The goal was to compute BP star of V of 1 smash THH of K of FQ be completed. And I'm going to get sick of writing this object, so it turns out that this is actually equivalent to the P-complete image of J spectrum, the same P-complete image of J spectrum I talked about earlier. So I'm just going to write J for that. Okay, so then let me do a proposition. So if you can compute this, and it's not too bad. You get polynomial on T1 to the P, T2, T3, and so on, tensor exterior on this element B, tensor exterior on lambda 1 prime, lambda 2, tensor polynomial on U2, tensor divided power on sigma B. So lambda 1 prime is sigma of T1 to the P, and lambda 2 is sigma of T2, and then mu2 is really sigma of tau2, which tau2 doesn't appear here, but yeah, that's sort of an artifact of the fact that tau2 is in the homology of J. Okay, so how do you prove that? Let me just do a proof sketch again. But the idea is that you can look at oh wait, so the input of the THH main spectral sequence is going to look like this. This is so this is actually an HFP algebra. And that's really nice because that tells you it includes into the co-module primitives. And then the other nice thing is that this spectrum on the bottom, or these groups on the bottom, are actually known. So this is known due to Engelveit-Rogness. And then, so this converges to EP star V of 1, the thing we want. And so it turns out that actually we get really lucky in this case. And these are E1 pages, I should say. And so this includes on the E1 page, and we know all the differentials here. And then actually, even after the E2 page, it's going to include again, and then this is going to collapse. So that's going to really be the whole story. So, so this computation it's significantly easier than if you just did mod p v1 THH of mj, which, yeah, you see me talk about that before. Okay, so great. So that's not too bad. And then we really need to know something about the homotopy fixed points as well. So you have a homotopy fixed point spectral sequence going from BP star V of 1. Let me just write T0, so that's really THH of K theory of finite fields, or MJ. And then this is going to converge to, so we're going to put less than or equal to K here so that this converges to BP star V of 1 smash TK. And one of the reasons actually that we work with these TKs instead of the whole homotopy S1 fixed points is that I don't really want to deal with working with continuous BP star here. So that fixes that fact. So let me not go into that, but yeah, so this avoids working with continuous BP star cohomologies. Okay, so this spectral sequence, what does it look like? Well, it's like if you took the homotopy fixed point spectral sequence, so that's going to look like this. I'm using the Serre grading here. So in each of these columns, you have BP star V of 1 smash T0, and then we're just truncating at some stage. Okay, so that's what the spectral sequence looks like. All right, so we need to know at least the D2 differentials. And so a nice reference for this is Bruner-Rognus. I think it might have been known before then, but I'm not totally sure. But D2 of X is equal to T sigma X. So you can use this fact. And then that tells you that, that tells you the E4 page. And then we're really only going to use the fact that BP star V of 1 smash TK is a subquotient of E4 up to extensions. So that's going to turn out to be enough for our purposes. I'd really like to say more, and I think I know basically everything that happens here except for what happens to the divided power elements. We had that divided power on sigma b, and there's still like something I'm trying to figure out there. So, but this is enough for the result I'm going to talk about today. Okay, so now let me return to the proof of the main theorem. All right, so we were looking at this unit map from S into V of 1 smash TK. And now we have X BP star. We have the induced map of Adams-Novikov spectral sequences. Okay, and now we need to have a specific representative for beta K in here. So this is in the green book. So beta K is represented by this element. So it's, let's say, well, first let me just say that beta 1 is represented by this element B10, which is equal to the sum from I equals 1 to P minus 1. And then 1 over P choose I, T1 to the P minus I tensor T1, at least mod P and V1. And then beta T for T greater than or equal to 2 is represented by this element. So it's K choose 2, K0, V2 to the K minus 2 plus K B10 V2 to the K minus 1, where K0 is this element 2 T1 to the P tensor T2 minus 2 T1 to the P tensor T1 to the P plus 1 plus plus T1 to the 2p tensor T1. And again, this is true mod P and V1. Okay, so let me give this whole thing a name. Let me call this beta T bar. Okay, so beta T bar is going to map to k choose 2, k0, and then V2 is actually not going to, so V2 is not in degree 0 in the cobar complex here, but instead you have T mu, which takes the place of V2, which is something you can prove, sort of putting something under the rug here, but okay, so, oh shoot, sorry, I just realized that these K's should be T's. Okay. Okay, so this is a T B10 T mu to the T minus 1. Okay. So this maps to this, and now this is a infinite cycle, by which I mean that dr of it is going to be 0 for all r. Sorry about that. So dr of this element is 0 for all r. That implies dr of this is 0 for all r as well. And so we just need to check if it's a boundary. And now this is the key, the key reason why we're using the BP atom spectral sequence. So note that this is in Adams Novikov filtration 2. So if it was in higher filtration, that would make this a lot harder. So then let me spare the details, but there's a long, tedious check shows that this is not a boundary. And so this element is actually detected. And so what is it detected by? So then beta T is going to actually go to, I can actually say what it is. It's going to go to T choose 2 T lambda 1 prime lambda 2 times T mu to the T minus 2 plus T times, sorry. Oh shoot, I have 2 different T's now. Sorry, I need a different name for this. So this T, yeah. So this T here is going to be the generator of the cohomology of S1, where you regard it as a group. So this is, which is polynomial on T. It's the cohomology of CP infinity. Right? Okay, so then, right. Okay, so then we have this plus S T sigma B times T mu to the S minus 1. Okay, so that's the actual element that it maps to in V of 1 star T K plus 1. All right, so, right. Am I, well, let's see. Okay, I'm close to time. Okay, good.
Yeah, we should wrap it up here in the next couple of minutes.
Sounds good. Yeah, I'm about done. So, okay, so let me just talk about the corollary. So so this is the end of the proof. The corollary is the following. So we want to look at the map from, well, we want to understand the map from this to K theory of Z. So we look at the map from this to homotopy groups of V of 1 smash TK plus 1, and we saw that beta K mapped to something I'll call beta K tilde here. And so then we use the fact that this is a commutative ring spectrum and the map, so this is going to factor through the map from TC negative of K of FQ. So this is, all these maps are ring spectrum maps. And then this is going to factor then through V of 1 smash K of K of FQ, again, because this is a map of ring spectra. And then you can further refine that to homotopy groups of K of FQ, and then use the commutative ring map from Z to FQ to get the homotopy, to get it to map here. So then beta K is going to pull back to something here. We call it double tilde. So the key fact is that all of these are ring spectrum maps, and this is the unit map. So that implies that it's going to pull back there. Okay, so that's basically the proof of the corollary. And so let me end by just suggesting some kind of future vistas, I guess. So I think that this result makes the case that if we want to study modular forms, we should want to understand more generally iterated K-theory of rings of integers and number fields. I think that this is something that deserves further explanation. So, my guess at this point is that if you look at iterated K-theory of these rings of integers and number fields, then you'll be able to detect even more information about modular forms and say more. And I think my theorem is like a first kind of step in that direction. So maybe I'll end with that.
Okay, I'm going to unmute everyone so we can thank him. Okay, and now I'm going to mute everyone again, and then I will, and then if there are questions, I'll unmute Gabe. If there are questions.
Hi, this is Sean. I have a question.
Yeah.
In light of the recent work of, I think it's Dustin Clausen, Akil Matthews, Justin Noel, and Nico Naumann about how algebraic K-theory increases chromatic complexity by at most one. Have you thought about looking to see if the gamma family is detected just in K of Z, using similar methods, but then looking at the gamma family, but not 3 times iterated K-theory?
Yeah, no, I haven't looked at that yet. That's a good question, though. I mean, my expectation is that it won't be, but yeah, I think I should. It'd be interesting to know if it didn't, and like why not. Yeah.
I have a second question. You said that it was key that you had all of these maps being maps of commutative ring spectra in the last large diagram that you drew. Is that
ring spectra at least? Yeah. Because the V of
I mean, they are all maps of commutative ring spectra.
V of 1's not a commutative ring spectrum.
Oh, V of 1's not, right. Okay, so the V of 1 localization is the thing. So where do you need that they're maps of ring spectra? Where do you use that?
Just because, so this element maps to here the fact that beta K maps to this under the unit map of the sphere spectrum means that this map is going to factor through all of these. I mean, you really just needed the factorization.
Okay.
Yeah.
All right, it's not like some part of the spectral sequence argument requires it or something like that. Okay.
No, I mean, I guess, so for the spectral sequence, like for the THHMA spectral sequence, at the moment, it's defined for commutative ring spectra, so we needed it, at least the input to be commutative for that, but yeah, other than that, that's not what's at play here, I guess.
All right, thanks.
Yeah, no problem.
Okay, other questions? Well, I wanted to make one comment or question about, so Prasid asked that question earlier about the inverse limit of the K-theories, right? And so, it's sort of, if all of these VN periodic phenomena are being detected by these sort of like iterated K-theories,
right.
I mean, I guess I haven't thought this through carefully. I'm just sort of like making this up as I go along. But isn't that kind of saying that sort of everything is then everything would be detected at some stage of that tower? And so, you know, that's just the homotopy limit is then the sphere or something. I mean,
yeah, that would be interesting. Yeah, what's let me phrase this as a question. So, so what is the homotopy groups of the fiber? Like you could look at the map of homotopy groups of this to the limit of iterating kn times.
Right.
Yeah, and yeah, maybe there's nothing. I'm not sure. I think that's also an interesting question.
Yeah, I mean,
I wonder if there's ways of, I don't really know good tools for studying this thing.
Yeah, I haven't the foggiest idea what you would do about it. I just was thinking about what, you know, that strikes me as like a hard maybe, but sort of interesting question.
Can I add another question in that case? Like, what will be the fiber kn locally, or like in some localized world?
Right.
You know, if it is 0 or non-zero.
Right.
I mean, if the redshift conjecture is true, I guess how does kn localization behave with these inverse limits?
Yeah, so that's an issue. In general, you have to worry about kn localization not necessarily commuting with inverse limits. Right. So Andrew Salch, I believe, has some work in progress on this. Where we've been kind of talking about this kind of question, but I don't know if it would apply in this case. So, but yeah, that's another consideration, sure.
Okay. Other questions? Okay, I'm going to unmute everyone. We can thank Gabe one last time. Okay, and the next meeting of the seminar is not for 4 weeks. We have a session off in 2 weeks. So we are meeting again at the end of February, and Martin Franklin from the University of Regina will be speaking. Okay, see you all then. Thanks, everyone.